Okay. All right. Now I think that we're live. Yep. We made it. All right. Everything worked well and we're both out here. So hello, everybody, and welcome to the latest Ultralytics live session. I am Glenn Jocker, your host and the founder at Ultralytics, and I'm here with Raymond Lowe at Intel. And we are here to talk about OpenVINO, acceleration of YOLO V8 models, a little bit about the technical details, and we've got some cool demos. And yeah, all right, so let's get started. So I'll give a bit of background, first of all, about myself. So I am a super AI enthusiast. I got started about 3 to 4 years ago, and I worked on porting over YOLO models from the darknet architecture, which was the original one they were created in by the original author, Joseph Redman, over to PyTorch, which was something easier that I could work with, that I could learn from. And I've spent, ever since then, the last 3 to 4 years, really working on making them better, making them easier to use, and helping them plug in effectively into all the other tools out there in the AI ecosystem. And a really key one is OpenVINO. It's one of the ways that you can take a trained PyTorch model and run it in deployments, say on an edge device. And in this way, you get much faster speeds than a PyTorch model itself. So this is something that took me a few years to realize. I didn't go to school for ML. I don't have a PhD. And for the first couple of years, I wasn't really sure what all this deployment stuff was about. I was busy with PyTorch. I was training a model. And then it was done training, I just run inference right there with PyTorch. So this worked well for me for a couple of years. And then I started realizing there's this whole other world of export formats, deployment, and there's much more performance that you can be had by taking that trained PyTorch model, exporting it to a more suitable format for your edge device. And this will let you save a lot of energy, run on lower power devices, and either run the same model at a higher frame rate or maybe a higher image size, or maybe for the same frame rate, run a larger, more accurate model. So Raymond, tell us a little bit about how you got started over there at Intel, and I guess bring us up to speed with what Intel is doing these days with OpenVINO.
Yeah, I like your story because I love you're very hands-on building tools. I can almost run back to all the way in school where I first encountered computer vision. I don't know anyone here remember the back old days where we do face detection, right? Just getting that little face cropped and figure out from an image was fascinating. So that's how I got started too. In school, I learned all the computer visions in class, and then very luckily I have the opportunity to do master and PhD on that topic. And I focus on one thing at that time in my PhD is how to get the most performance out from something that runs well, but not good enough for everybody to use. So I was optimizing one thing called HDR video. So back then, you know, your phone barely takes photos. I was thinking, it's not that great quality, but with a processor, right? Why don't I process my image, make it better? So I built apps, I built even eyeglasses at that time to process image in real time. So I figured out Intel at that time was doing OpenCV. Anyone heard about OpenCV? Yes, right? So you know how I learned optimization? I read the source code from scratch. That was not fun. So you read all the pipeline end to end, MMX, SSE. And after that, once it get to the performance, then because like the big difference were 15 FPS to 60. So my professor was like, it's really smooth. How do you do that? Don't ask, right? I spent many months like optimizing it. But that's why when I joined Intel, I almost want to resonate with Glenn's story is sometimes it matters, right? That 2 to 3x is what you create and define experience. So when I joined Intel, I saw a tool called OpenVINO. Again, before I joined, I was a CTO of a company doing augmented reality. So I still love like those latency stuff. But when I joined, I was like, wow, I think we can do something in scale now because very luckily Intel have a lot of processor. If you ask me like how many x86 processor are in this world, I don't know, but I can tell you there's something somewhere maybe in a supermarket they're running it. And then having OpenVINO doing the optimization, having the energy reduced, having the performance increase, I find it quite interesting, and there's a community behind it. And that's why I'm here. I started as a PhD student, do my company in the Silicon Valley, joined Samsung, Google, then I landed at Intel as an evangelism and also doing a bit of management at Intel.
Okay, awesome. That's an interesting journey.
Yeah.
Mine's a little different. I got started in engineering, aerospace engineering. I originally wanted to be a pilot, and it turns out that I'm terrified of flying, and so I had to find an alternate career path. And so I ended up at a few engineering jobs before I started doing particle physics, which is how I founded Ultralytics. And then it was there on the data analysis side of particle physics that I really started using ML, sort of out of desperation to try and get better results. And it didn't work very well, but I noticed that there was this wide open world of exciting things going on. And that's where I've been living in the last 4 or 5 years. So now it seems like we're having much more success with vision models, computer vision models. And I think we are really making a big impact on society, which is something that I always felt I was missing kind of earlier in my career. So okay. So you say these OpenVINO export formats are more efficient, they're faster. Do you have any examples or numbers to back this up?
Yeah, so I do prepare a deck today to talk about it. But I think the first step is to think about why this exists. I talked to some of the engineering backstory from Intel. I think a lot of people want to know, how do we get started, right? And then the number shows at the end, because when we started, I talked to the founding member of OpenVINO. We started as like a computer vision tool, again, like a CV library, but it's more on the deep learning side. I think about 6-7 years ago, remember machine learning, deep learning is like becomes really interesting. And at that time, folks already working on it. And then they try to deploy this on not a normal computer. It's almost funny. It's on a printer. There's a very good processor in a printer. So they started like porting this all together. And then they figured that for printer, you need to make sure that it runs on these tiny chips, right? And then that chips are very constrained. So they start putting all this together in a way that, okay, back then, remember PyTorch, TensorFlow, Caffe, Keras, and all that. So a lot of customers want to know, how can I get the best performance when these models are coming out from the community and make sure that it runs on the hardware? So that's what it brings that journey together, because in the beginning, it runs on of course, the CPU, and then some of that specialized processor. Then we start to expand the scope as we go. Now we talk about GPUs, right? The iGPU. Does anyone know you have a processor called iGPU as well?
Now, I think you need to explain that at some point here, because I'm a little confused.
So the integrated graphics card. So I think the one that does, okay, I gotta say it, Intel. The back to old days, the one that doesn't play games very well, remember? But they do parallel processing extremely well. So if you're doing video encoding with it, you're doing a lot of tasks with it, they're very capable actually. So and
every Intel CPU has one of these?
Almost like most of them has it, because like they just like a bundle, right? The iGPU and the CPU come together. So so that's the Intel integrated graphics kicked in. And then having that leverage as an accelerator and then keep expanding the scope, I think this created kind of almost a hybrid architecture to me. Like you can switch between as needed and then tapping onto resources that you already have. And that's why the number is 1, but that flexibility is what I think makes it interesting talk. And I do have a set of slides to show you if anyone interested.
Okay, awesome. Yeah, let's take a look at them.
Yeah. All right. So now I have to learn how to share my screen. 1 second.
All right. So
I want to make sure.
See on the bottom. Yeah, we should have this green share arrow there.
Making sure it's sharing the right thing.
Ooh, I see it.
All right. Okay, perfect. Okay. So 1 second. Make sure this is.
By the way, Raymond, it looks like the Vino is capitalized. So in Spanish, that means wine.
Wine,
what does that mean here? I don't think it means the same thing.
So it means I'll talk about what it means. That's the joke we put together, like OpenVINO, open some wine. But it's not. VINO stands for Visual Inference Neural Network Optimization. And I think today we went above and beyond on that. But yeah, so that's what it stands for. Before I start, I think the story I want to tell is I'm not alone. So if you're talking to me today, but you're not in the same region, you can feel free to reach out to our team around the globe. So any of them there will be able to answer questions like I do. But you can see we do have a very interesting group here. So I went through Y Combinator, for example. I did startups, and then I have researcher, professor, even very hands-on people that did AI labs in the past. So feel free to reach out to any of them. Take a screenshot here.
Wow. Okay.
Yeah, so that's our
It's a
global
global
team right now.
organization. Yeah.
Yeah, it's Intel, so hopefully everyone in the globe can have access to it.
So how do you guys decide on a meeting time that makes everybody
Oh
happy?
my God, I'm 24/7 right now. That's see, you see
Yeah,
this right
me
here.
too.
So sleep is not an option. But I do have a scheduling philosophy I can talk about offline with you.
All right.
But yeah, so that's why we start the topic about CPU GPUs, right? Because something I noticed were as a developer, we always want to make choices that make sense, right? Of course, everyone wants something called a performance and power, very powerful, very quickly, right? Get 1,000 FPS. But in reality, remember my story, having that 60 FPS, right, was fundamental for my use case. So sometimes having CPU, GPU working together, maybe that is something you want to think about. Because that's what a philosophy is you don't have to be constrained when you think about what we're doing today in OpenFino, right? We can use any processor under the roof, right? I'll say we went even beyond Intel. So you can work with ARM, for example, if you really care. And that's what I think what keep the community excited. This is open source. So if you really want to port it to your own architecture, you can do it. But that's the thing that I think a lot of us want to learn this lesson is how do you get the best out of it? Because the last thing you want is what I did is remember my PhD, how I optimized? I opened the C++ library, read how they did it, and copy the chunk of code. Hopefully you port it over with no bugs, right? That's really hard, right? And then this very hardware optimized approach. And anyone did CUDA here? I don't know. You know how hard it is to learn at that time. So I learned it. So I actually took like 2 years of courses to figure that out. So that is not something very easy to do when they think about architecture, right? So cross architecture has been always the biggest pain, right? And lastly is what about edge use cases, right? Because the low power maybe is the performance thing that you care is having that 5 watt, right? You want this to be flying. Remember airplane? How big can you put a machine there, right? I think they have like restrictions that maybe less than 20 watt or 15 watt. You cannot put like a fan there because it's too hot, guys. You cannot like just assuming you can have enough cooling, right? So there's like a lot of use cases that actually has to make sense. That's why we have to really break that barrier, right? Skip those like curvy path and break into the direct solution where we provide optimization ground up. And that's part of the One API. I think some of you may have heard about One API. Have you heard about it? No,
haven't heard about it.
Now I have to explain it because a lot of people may not know. It's been running behind the scene for most of the work that a lot of us like doing scientific computing. We've been actually empowering like Panda even behind the scene to get that performance out, right? So when using that, if we didn't do the optimization, CPU may be in 5 to 10x slower, right? So there's something we have done. So we're leveraging that. And today I almost have to say, we work with generative AI, LLM, NLP, and audio as well. So we're quite expanding the scope right there. Because I think in the future, the inclusiveness is what makes this a very interesting tool. And any questions so far? I've been, on this journey. I gotta bring everyone to like how we think about optimization a little bit today.
Okay, sounds good. No, keep going. Or if anybody has any questions, feel free to leave them in the YouTube chat. We'll get to those later.
Right, and like for you, exactly. So today, if you're a developer, most likely, I would guess you're starting early still because this field is still maturing, right? There's a lot of like excitement happening. Like today,
it's changing so fast.
Yeah, it's like every day I feel like I am restarting my PhD as I felt, right? So like, it's like, oh, this like transformer new again. I was learning neural network, then all of a sudden there's a new idea, right? And then all this like, it's like my
before
head
you're done
like,
training one model, you have to cancel it and start with the new architecture that just came
out. So that's the pain of developer journey. I want to almost like put this almost like a joke. It's like it's never a straight line, right? There's always something. But fundamentally, you always want to start with some model that you want a problem statement to solve. Then you go for some optimization and deployment. Like what you said, right? something only runs on your machine, it's good as an experiment. But when you deploy, it's a completely different problem we have to figure out. So that's what brings us to this first is very diverse portfolio. As a bird eye view, this is how I see it right now. Like we can have all this architecture because even CPU, do we know that we have Xeon, Core, we have Atom? Anyone knows the difference? You know, remember they all CPU. So
I see you have ARM on there also now.
yeah, even ARM, right?
Yeah,
What's the difference under the hood? A lot of time people don't know, right? And to us, if you're doing optimization, the difference will be the instruction sets. We have AI accelerator, quote unquote AI accelerator is a term we use. Basically encapsulate how you can do, let's say, when you do convolution, it's like multiplying matrices, right? And how do you do multiplication faster? Doing parallel, right? So we even have that kind of like a pipeline processing inside the CPU that can do parallel compute. That's what the x86, right? The architecture is great for. And of course, yeah. Any questions there? Yeah, I think that's like
so. This is like multi-threaded. Like let's say I have like an 8-core CPU.
Yeah.
So the I guess like if OpenVINO is running on that CPU, then it'll parallelize up to say like 8 channels.
Yes, so that's part of it. So think about layer in a CPU, right? The basic fundamental is you have multiple cores, right? Then from there you can have hyperthreading. That it's not real core, right? It's actually 4 core, but you have 8 threads, so you have 8 logical cores. So you can put work on that. But when you do multi-threading, you're just like interleaving between 2 processes, right? Yeah, 2 threads. Okay. But under the hood of that CPU, let's say you have the same process. You want to multiply 2 arrays, let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. You want to multiply them. Yeah. You can have a single clock to multiply them together. That's the trick. It's like, hey, so you have a function call that actually can run 4 times faster because under the CPU, it'll parallelize again. We call it pipelining, right? So the technology we call is called the VNNI. Oh dear God, acronyms again. Let me remember this. Vector neural network instructions or something. Anyway, so a lot of that came out to be the core reason why you can get 2x faster by doing optimization, right? Leveraging these kind of instruction set, right? And even more than 2x, depending on what you're doing. Yep. Yep. All right. And CPU, you can beat it to death. There's so much going on, and I would love to give a talk about just what CPU can do. But on the GPU is what's new to us, right? Remember we talked about integrated graphics today?
That's right.
We have
here it is.
Yeah,
Iris, right?
That's the Iris, right? They actually play games now. I'm actually pretty impressed. So I can play some modern game on it a little bit better. But the Arc is where it really, I think, we're very new to the market. Last year we're shipping, and probably what OpenVINO can do today is it actually runs some of their like generative AI, YOLO VA, all the good stuff, all the goodie on this hardware. I think we recently played with it. The number was like, what's happening, right? Is in the class of like speed that we can get right there.
Yeah, we did some benchmarks on that, and it was very fast. Yeah. Yeah,
and then of course you have data center. That's a service class, and I think it's important if you're, let's say, building a business, right? The last thing you want is put a gaming graphics card and it burn out the night over, right? So we have a more serious approach that have better cooling, not better cooling, proper cooling for the server setup. So then you can actually build a rack out from it. And then beyond that, we have PPU and FPGA, which I think I'll leave it to the next time because we have some announcement coming up.
Okay.
Yeah.
This is an impressive list, but there's one thing missing, I think. What about Intel's Habana effort?
Oh my God! You asked me the hard question.
Where does that slide in here? Yeah.
So
that was
we
the Habana team.
So that's a very good point. We do expanding that before, and then we have some discussion. So right now is if you talk to our team, we'll give you some information more, but it will be a little bit behind the scene under NDA still. So if anyone interested, do reach out to us, and we can talk about our progression there. Sounds good?
Okay.
Yep.
All
right. And the lovely thing is I'm a Linux user. I use a Mac right now. And too, Windows. Yeah. So this is the part that if you're a developer, could be flexible. So that's the high level of what OpenVINO can do. But today I think I want to talk about one topic, if we have time, is like how you squeeze all the performance out from the same model, but by changing a couple bits and bytes here. And that's, we call it the quantizations. Do we have time for that one? Maybe a little bit. Maybe 10 minutes of education today. I'm not sure what that will be.
Yeah, I'm interested.
Yeah, okay. So, so today I hope I don't bore everybody because this is like almost like a lecture I'm giving right now. But the idea is when you think about optimization, if you're a developer, the last thing you want is DIY. I did it, so I don't want to do it again. Because like having this optimization require a lot of testing. So here we have two things that we test pretty extensively. One is like converting the model. So remember we talked about having those model in Onyx, in maybe PyTorch. When you're trying to do deployment, it's quite messy sometimes, right? So first it's like we did the conversion and also the compression. So that trim the model a little bit, cut the fat out. And also you can do the pre-processing in the model. The other one is like compression. NNCF is like neural network compression framework. So this is the one that I think eventually we will have a class about it because that's where you get the, how remember the pipeline in CPU? Once you compress the model correctly, you can, it's like unboxing some sort of secret weapon kind of stuff, right? It's like, boom, like 3x
where the real
more stronger.
Increases.
Yeah, so that's like how I see this in a gaming perspective. So, but in the runtime, this is all it takes to run something. 6 lines of code, pretty much. That is fundamentally how it looked like. You import the runtime. You have the model that's been converted, and you define where to run it. Remember how I say running on CPU, GPU is very different architecture? For us, we handle it by having a plugin architecture. So if you change the device name from CPU to GPU, it will run most of the time. And there's some caveat. I'll talk about the catch a little bit. So this is number one, I think, for us to learn is when you optimize something with OpenVINO, like when you optimize the model, the optimization also help the portability, right? That's step one, right? So you can now have cross-platform. And then the second thing we do is like, we create the logic so that you don't have to deal with what hardware you're doing. So remember the use case sometimes is you have CPU and GPU, like a hybrid or maybe multiple devices. So we have something called auto plugin. So which is basically, okay, you have a machine, you have a laptop, you don't know what the spec look like, but you have maybe Intel Arc with the iGPU, with the CPU, you'll figure out how to use the best of. So as a developer, you don't want to deal with, let's say, the hardware side, then we will help you to make the judgment. The best guess, right? Usually we'll pick the best performing one and ensure that the user experience is great.
So this is great. This is what we have with YOLO V8 right now too. We've set device name equals auto. So when you're running an OpenVINO model, it'll just pick the best backend for you.
And of course, to the catches, there's a bit of like, depending on what you want to do, there's a little bit of the lag in the beginning, the first 10 frame, 100 frame, trying to figure out where the things you want to find, like how to put the resource. So there's a bit of trade-off, but to be honest, if you're running like a video stream, it should not matter to you because it will discover and find the best device for you. But single image, be warned. Okay.
Yeah, this is something I've seen with a lot of formats, and I think PyTorch also. There's a bit of optimization, maybe some just-in-time compilation that happens the first time, or even the first several times you pass an image in.
Well, let's take a mini break here, is because when we talk about optimization, this keeps me awake at night. Basically, it's so hard. So you talk about first scheduling as one of the many ways to optimize, right? About shared memory, caching, batching, pre and post processing, asynchronous. So when we think of optimization as a company, right? When I work with my engineering team, I always find that we have to almost have like 20 teams to work on this problem because they all are very important to some piece of the puzzle, but there's no one single answer. It's not like the single mix of ice cream. Even ice cream have 1,000 favorite kind of problem I'm dealing with. So this is a mixed problem that we have to deal with. But the tool we provide give you access to each of this. Like for example, shared memory model caching, there's a specific library called we actually handle that because like model caching is very important for load time, for example, we talk about. Like remember the first time just to get that model up and running, it takes so long. But we can cache it. We forgot about it. We can cache because you don't need to do the compute twice if it's the same thing, right? So that's something we can do. And that's why I think for us, making these kind of even precision choices. I'll tell a little story because I did my computer science at that time. The first thing we learned is how to define a variable called innate, float, double, long. To me, it makes no sense at that time. It's a number. What's the difference, right? So that's the first like computer science 101 exercise. Just like make a program to add some number. And guess what? Once I get deeper into neural network inferencing pipeline, every addition adds up so quickly, right? Every multiplication. So precision matters because I learned by so in A is so much faster, for example, but fundamentally in the chips, it only takes 8 bits, right, to store it, and we compute it, use less memory. And floating point is very expensive. And floating point have two types, right? The 16 and 32 bits, right? And then for computer vision tasks, a lot of times 16 is pretty good. It's all you need. You don't need like 32 bits.
16 works pretty well. But you've got a different kind of 16 here also in your chart. Something called BF16.
You pick about the new one I was talking about. BF stands for it's the format that created by Google. We collaborating with Google. It's called a brain floating point. It's like brain format. Brain is like the brain. BF, right? So what it does is I gotta go a little bit in detail. In floating point, let's say 32 bits, like basically it's 32 bits of space you can store information. A chunk of that goes to the exponential side. So every single number represented is like, like 1.25555 times 10 to the something. That's how you represent a number in floating point. So a chunk of that goes to exponential, exponent, and there's like a significant figures, right? That's like how you represent a digit. But when you come to FP16, your exponential gets a lot smaller, right? So what happens when you're doing neural network computation is it can get overflow. Like when you multiply two number, it gets too big. The computer, like for example, the computer can only store like 2 bits, right? Ceiling. When you go precision, go above, then overflow. So what we have observed is the significant figure is less important than the exponential. Like when you're doing a lot of those computation, you multiply a lot. The last thing you need to worry is like, because when you're doing training and all that, you're estimating anyway, right? You're guessing the trajectory. It's like you're going this way, but you're off by a tiny bit, it's okay. But if you have exponential, that's too, it's like off, then you're basically going the back direction. When you're doing the propagation, you went backward. So that's why this format existed and become a standard in our new hardware. And I can have a whole talk about it. It's super cool.
So BF16 simply allocates more bits to the exponent and less to
exponents. Yep. And that matters in the compute. Yep. In the computation, because you don't have to deal with the overflow as much. And it's very stable in training as well. So beyond inference, when you do training with this format, which is a standard coming up, and then you see.
It's always one of the dangers. So YOLOv has AMP, automatic mixed precision, which runs some operations at FP16, but for certain architectures, it's a little less stable. So you have to be careful.
That's why you have to learn your hardware and the software design. That's the trick. And as you see, right, this is like why this is very important for developer today to figure out, okay, what optimization means to you. Then the other thing I think a lot of us missed out is for computer vision tasks, you don't have to wait. You can do things in a better way. So when I say you don't have to wait is you may have like get a frame from a camera, you do the inference, then you have to wait for the next frame, and there's some idle time, there's you do the next inference. You can do this in an asynchronous way, and then having camera and the inference working in a more like directly parallel to each other. That takes a lot of time to code it together properly. So the asynchronous API is non-trivial. I think I teach operating system at one point in class. It was not fun. So and this is actually very important because you remember I say how to get 2x faster sometimes? Don't wait. That's my answer here. Sometimes the camera waiting more than actually doing work. So that's another way to utilizing your resource carefully. Again, for the coding perspective, I'll share the deck later. It's not bad. It's a callback function that you can just define and then you set the queue. So it's very object-oriented programming for you. It's not that hard. Better than when I started as a student. So, but what we really care today is we don't want to like overpromise you that performance tricks just works with one, but it's really about having that matrix before and then having your favorite come together for your hardware. So, for example, today, if you have let's say your native PyTorch model, if you do what we give you, like say with all this latency mode, the share memory, all this goodie, you can get very much like double sometimes, right? Depending on the model, again, disclaimer, depending on your model, but definitely you can get a lot faster from what you already have, right? Without even changing much of the model. And that's like step one, right? Because remember, a lot of time for demo is really hitting that magical number, maybe 60, 120 FPS for your use cases. So this is like a very good starter for us.
Yeah.
Right.
Yeah.
So I gotta start the next topic, but any questions so far? Stop. I think the stopping point is great because this is getting harder now.
No, I'm learning a lot. This is good stuff.
Yeah. So yeah. So once we understand, you can do all the mixed bag of like having the same model, but you have one moment in life you realize, let's go back to easier way is using less to do the same work. So remember how I talked about in computer science, we use integer to multiply to number, get the results. And let's say you multiply 8 times 8, right? 64. And using float, 8.0 times 8.0, right? It's a lot of continuum, right? Floating point is continuum. But you can get same answer or very similar answer if there's like, you can, massage quantization to do the work. And that's happening in the camera system today. Anyone still using the camera today? The cell phone, sorry, I shouldn't be branding it. But but you have a cell phone, you take picture, they're all quantized, right? So you already stored it in JPEG. JPEG is only 24 bits. So so 3 channel, 8 bits per channel. So fundamentally, all the tiny pixel are represented by 0 to 255 and 0 to 255 per color, right? And when you look at it, it looks so good. And today you have 10 bits, maybe 12 bits for HDR, for even more. But fundamentally, they are still quantized numbers. And that's a very important concept that a lot of people forgot, because when you do quantization, it's non-trivial, but you can now compress your model to do the same work close to, but with a lot less resource. And there's 2 times you can do this. When you first way is you have the model finish training. And then you want to figure out, okay, I want to compress the model. So what you need is you cannot do it blindly because you don't know the behavior, right? So you need to provide a small subset of data. So think about this, right? When you try to compress something, right, you have to know what's lost. What's the loss? Right? You have to calculate the loss, right? How do you calculate loss? You have to have a ground truth for some way, right? So you have to give some data that represent, this is like the behavior we want. So every time I take away something, am I breaking the system, right? So this is called a post-training quantization that we're doing today. So that's the easy path, because as long as you already know what model you're using, you get some data. And we have a demo example in the notebooks I will share at the end of the day with Glenn, and you can have it for the audience. And I'll teach you how to do basically called a post-training quantization. So you don't need to take the model from scratch and retrain it. You just like modify it. And the benefit is you can see the pipeline. Now you're working with innate, which is a lot smaller.
Right. So the calibration is this is an interesting thing that I had to learn about for a while.
Right.
So since there's different methods to, let's say you have a layer, right? And let's say you have like 10,000 weights in the layer. Then if you make a histogram of what those values are, those could be over a wide range or over a small range.
Yes.
And they're probably going to be biased a little bit. And so if you say had to bin that into 255 bins for like an in-date lookup table, then it helps to pass a few representative images through your model to see what kind of values are coming out of that layer. And so this is where like your representative data set here comes into play. So this would be basically really similar to what you trained on or your validation set. You pass those same kind of images, and this way it can kind of tweak those calibration constants in that lookup table to just I think like really utilize that dynamic range the best. So it's a little tricky, and you don't need the screen part, but it helps. If it doesn't have the green part, then it just has to guess a dynamic range, I think, using some sort of this is your validation set.
Right. So if you don't have it, you basically like throwing it like to the wild and hope it will work. So that's exactly the same thing, right? If you know that distribution, now we can control the accuracy a little bit. And again, we're oversimplifying it, but I think for the audience, think about how you can pick the best likely number that would not break, right? So this validation set, having that allowance. So you, if you're critical on the accuracy, let's say you need to hit the 99% for whatever reasons, you don't want to drop that. You can preserve that layer because you can see each layer how it behaves. when it switched
Oh,
the
so it's
position.
smart. So it'll keep that. Yeah, yeah. If it sees it as the critical
So
layer.
you can say, hey, don't touch it. Every time I touch it, it exploded, right? So something doesn't work. So this is actually one way that you can control it. And you can do it with the like different flag, It's not as simple in the beginning when I use it, but today we have a better API, and I'll show you an example at the very end. So this is like some of the detail how this work, right? Like what you said, right? You pass it through back in and out, just figure out what the way looks like. And this is a set of things that we are shipping today. So we talk about post-training, we have the accuracy control, we have the quantization aware, pruning, binarization, sparsity. What does it mean? A lot of them still sounds like magic to all of us. But when you get deep into each of them, I have a documentation. It's not that bad. It's just a set of error from that really just like to, for example, pruning is right. You want to reduce.
Yeah. I think I recognize everything except for binarize. It's the first time.
Binarization, right? Maybe it works with a mask 0 and 1, right?
So yeah. So is this turning the entire model into a binary?
No. Like usually by layer by layer. Some layer.
Okay, so occasionally a layer. Yeah, I got you. Okay.
Right, or some of the maybe later, maybe it's less layer.
So this is almost like yeah. So this would be like almost like 2-bit instead of like in data, it'd be like almost like in 2.
Yeah.
Okay.
Yeah, that's right. So I think in short, the programming, right? How does it look like? Pretty much this is how it works. You load the model, do the pre-processing of the labels and all that, just making sure it's clean. Then you run the quantization step. Then the rest is just basically you'll get a quantized model that you can save it. And then that's like pretty much all the code that we have to think about. Again, load the model, load the data set, and then push it through the quantizations. And that's important for a lot of, let's say, industry today, we realize is, for example, in retail, they cannot put a machine up high with like a fan. It's a real problem. And then for people tracking, let's say for people tracking, pedestrian tracking, it works extremely well for this type of use cases because as long as you see like 96%, of that, the accuracy, even a 95.9 is okay, right? So they're not very accuracy dependent, but they're very performance dependent problems. So these are the very interesting observation we made is how bad is it, right?
How much do you lose in the process?
Yeah, like do I lose a lot of like accuracy? Like oftentimes if it's not bad, they're surprisingly good. Again, depending on data set, depending on your model, depending on use case. But oftentimes we see a performance that I think we can just accept it as like a deployable solution. Again, this is like one example
that I would say. So everything that you do is really compromised. And I think like in this kind of case, you could see that a small accuracy drop buys you a significant inference advantage in speed, thermal consideration. So it's always a trade-off when you're designing a system, and like this kind of trade-off, I think is definitely worth it.
And for Xeon processor, this is 3 to 4x easily. Like again, based on the architecture. Look at architecture together because we have something called the AMX and all that.
And so this is like real money that you'd be saving. So this would be electricity that you're not paying, possibly cheaper hardware that you can buy to deploy this at scale. And so on. So this is like real impactful to a bottom line in commercial applications.
Right. And the nice thing is we also work with our quantized model coming up, right? So let's say you're quantized in, but many people work on this. This is a very well-known and useful problem, right? So our runtime will also take different model as we moving forward. So that's something I think is really cool because without this kind of collaboration with the whole community, like we would never get there. So again, if your problem statement is tracking the bird, I don't see a difference in real world situation. Left or right, I don't know. Where's the bird? The birds are there, but it's off by maybe a tiny bit, 0.26. Still a bird. Okay, so this is a duck, by the way. So and another thing is we also see in different solutions like Pose, right? And this is the major difference because when you're doing interactive solution, right, 40 and 80 is a huge difference. It's like basically usable, not usable in user interaction. And then also look at the model size, right? It's a lot smaller. So if you have an edge device that, let's say you're doing yoga pose, right? And then you don't miss the pose, right? That's how.
Right. And if you're doing a tracking layer on top of these, then that'll work much better also at a higher frame rate. So.
Oh, now we're talking. I have a demo right there on the right side. All right. But you already, so today, I think the bringing message is we have all this method that we solved and created. And now, if you want to go really hardcore, this is like really above the line. Post training is only so much you can do. We call it like, it's like after the fact problem, right? It's like, I've done the model, right? Now fix it, right? We can actually do it from the beginning, right? So when you're doing training, we are aware of which part of how you're building the model, how you define the layer. You are looking into that since kind of the beginning of the process. Now we can get even better fine tuning and all that stuff in the beginning. And this is what I would recommend people to do if you haven't started data yet. This can give you a very significant, even better in the accuracy part, right? Not just performance, the accuracy. And that's very important because if you can go from beginning to the end with the same mindset, then you don't have to throw the ball down the road and make someone else suffer later. That's programming 101. Don't leave the mess behind.
Right. So this is like a next level that we haven't gotten to yet, YOLO V8.
Yep.
But you're right. This is sort of like the ultimate step. If you can start your training with these processes in place, then you can benefit even more on your trained model.
And that's the hard part. Today, I was just like, okay, all right, let's look at the demo.
This part really takes a lot of, I think, deeper integration with training tools.
Right. Yeah. So today I would like to demonstrate the example that we put together at Intel using YOLO V8 and quantization and all the steps. You can see I'll show you the link of the notebooks later, but I'm gonna run a demo right now of me running this on a laptop. There's a very okay average gaming laptop I have a year ago. So what I do right now is I'm running this on my GPU, iGPU. That's all the processing happen on the Intel processor. And then I leave the CPU more resting so that you can do other things. And I combine this with a camera that has an AI built in so it can track me. Now you can think of a possibility. That's very cool. Right?
Yeah.
So
this is what I need for
multiple layer of AI. So now we can track you everywhere in the house. You can see your pose. And then and all the code is right here, right? So we define it in the GPU, and then that's it, right? So how do I do this right today? You can download it, you can try it, and then we have a repository that I will share the screen right after. And that's all it takes for you to learn and run optimize YOLO V8 model on your laptop today. Be warned, you need at least 16 gig of RAM, so just don't go too low on the RAM. It takes some RAM to optimize the model because you need to explore a little bit here.
Raymond,
but to run is a lot lower.
In the YouTube chat there, I think everybody will be able to get it there. But you're right. So you guys have got a lot of these Colab notebooks or Jupyter notebooks with really nice demos here.
Yep. So
more than us actually. But
So how much time we have?
Let's see. So we got a few minutes left. So let me do a little bit of show and tell. I think. I've got a few examples of how this is all integrated with YOLO V8. Now we made it really simple. So all right, let me try and share my desktop here. Boy, now it's my turn. Okay, so if we go to the Ultralytics repo, so we got two exciting things that we've just done. So we've worked with the Intel team to make really good docs. So this year I've almost been doing more docs than YOLO. So we've got hundreds of docs pages now for all the fun stuff you can do here. And we've got an entirely new section. So if you look here on this integration section, you click this, you can see the different tools that we've integrated with. And we started making more detailed pages over here. We've only got two so far. So OpenVINO is here at the top. It's one of the first pages that we worked on. And we've got great examples of how to export a model to OpenVINO, the settings you can use for that. So we've got much simpler settings than what you were showing, Raymond. We're still getting started on some things like int date and so on, but we're hopefully going to work on those later on this year. But the process is just very simple. So for example, if you want to export a model, it's just one line. So here we see a export command for a pre-trained model, one of these official models, YOLO v8n.pt. So if this model doesn't exist locally, then YOLO will just automatically download it. Or if you have a trained model that you've already done, then you simply point to it. It might be called best.pt, and you specify the format is OpenVINO, and you can pass these arguments. So you can pass a different image size, and you can also ask for FP16 quantization. So it's all just super simple. And then of course, once you've exported it, you're gonna want to use that somewhere. And that's this next line. So that's also just one line. So you can now run predictions with this same model. So if you export YOLO v8n.pt, it'll end up as a directory that contains, I think, an XML file and a bin file. So you just point to that directory, or you can also point to the XML file and a source. Here we've got an image, just bus.jpg, and it'll run inference with this OpenVINO model. And of course, that's great for a demo, but you're probably going to want to integrate this in a larger tool, and that's what we have our Python code for. And so the code there is just as simple. So you would create a PyTorch model here. You would just export this to OpenVINO, and then it's going to create this same directory. And then from there, you can load this using the same YOLO class as you load a PyTorch model. So the YOLO class is super flexible. It uses something behind the scenes called the auto backend class that I created. And the idea is that we want to make it just super, super simple to load models, no matter what format they're in. So if you export this model to any format, you can also load it using YOLO. So now we have this OpenVINO model, just super. And again, we just run inference, just passing the source. And now you'll get the results class. It'll give you all the coordinates, the boxes, and you can have methods on that, like results.annotate, so on to see your results, .save, .show. So we made all this just like really, really simple here. And we've also run some benchmarks that are here in the docs. So we wanted to know officially just how fast these models were. And like I've always expected this was going to come out really well, because in YOLO V8, we've got a lot of actions, and some of the actions test export models. And so we have what are called benchmarks here. So if you go into our Ultralytics CI and you click the benchmarks, we've got a few different jobs. And what the jobs do is they benchmark models on all export formats for different tasks like detection, segmentation, classification, and pose. And then we show a summary. So if I click the summary, kind of skip all these details and just jump straight to the results. What we see here is a table. And so this is for a detection model. So this is the same YOLO V8 Nano model. So we're benchmarking it on a really tiny data set. It's only got 8 images, and we're benchmarking it a really small size because we don't want to take all day here. And we have a lot of formats to do. But what we see, though, is we've got the size of the exported models here. So this is the PyTorch model in FP16, which is how we store the weights natively. And then we have the validation accuracy. And this is really good to show so that you make sure that the export format doesn't drop too much in accuracy. And then we also have the inference time. And so this is where it gets interesting. So if you just run inference using a PyTorch model, here at image size 160 pixels, it'll take about 18 milliseconds. And if you export that to TorchScript, for example, it's super slow. If you export to Onyx, you get a significant speed up. It only takes about 6 milliseconds. But if you export to OpenVINO, it's even faster. It'll run in about 5 milliseconds. And it's not just faster, it's also like the fastest format that we profile for. So we see that here for detection models. And then if we go down to segmentation models, then we see the same effect. So OpenVINO is again the fastest. Here we have classification models. It's again the fastest format. And then lastly, pose models. And it looks like it's also the fastest. So on these GitHub CI runners, we can see that it's definitely very fast. So we can look at the exact CPU that it's running by looking at some code here. So let me see if I can find something. Here we go. Okay, so these CI runners use all kinds of hardware, but in this case, it looks like they're using Intel Xeon chips. So the moral of the story seems to be that for Intel hardware, your best format that you're going to get the fastest results on with no drop in accuracy is definitely OpenVINO. And so we've got a docs page where we did a bit of a study here. We exported different formats. Let's see, PyTorch, TorchScript, Onyx, and OpenVINO. And as you were mentioning, Intel has a few different GPUs these days. And so we started with a Flex GPU. So this is the data center GPU that would be used for commercial applications. And OpenVINO here is the yellow line. And so we see just a great speed up compared to these other formats. This makes sense, of course, since we're pairing, I think, Intel hardware with Intel export format. And this is the Arc GPU, which is a more consumer offering. And we also see a pretty tremendous speed up here. So these little yellow, I don't know if you can see this, the yellow bar here is the speed for the OpenVINO format. So it's super fast. But I think more kind of after like the rest of us is the CPU world, because there's obviously a lot more CPUs out there than dedicated GPUs. And what we see is just like the CI runners that we were showing, the OpenVINO format is the fastest here on Xeon CPUs. And also more common are the Core CPUs. I think everybody's pretty familiar with these, like Core i5, Core i7. So we had a Core i7. Yeah. So we just had an HP laptop with a Core i7 here and 13th generation. And we see that it's significantly faster than, for example, Onyx exports or TorchScript.
That's right.
So, and this is just plain vanilla. Everything's in FP32. We haven't done any of those fancy words that you were showing before, like quantization aware training or binarization or any of that fun stuff. We're going to work on that later. But even with just the simple integration that we've done right now, we're seeing a significant speed up. So it looks like if you have Intel hardware to deploy on, then OpenVINO is definitely the format that you want to use.
Great to see. It's fresh off it's just merged. I remember the PR just 2 days ago.
Yeah, we just got this done. Yeah. And if you guys would like to reproduce our results, we made that super simple too. There's actually, again, it's just one line here. I'm a big fan of one line. So, so you can run this on your local machine and it will run the same tests and it won't make the plots, but it'll give you a table like you saw in the CI here. So you guys should be able to kind of like recreate this table on your local machine and kind of see what this looks like on your preferred deployment destination. So
that's great. I really appreciate all the hard work there because we go back and forth just getting the right hardware. I remember all the journey behind the scene. Thank you again.
Yeah, of course. And thank you for helping us get this integrated. So let's see. So we're running up on the hour here. So let me switch over to YouTube and see what kind of questions we've got. All right. So okay, we've got a little list here. So okay, let me start with the top. So we've got Helm Me Code Camp says, "You're awesome, Glenn. Keep up the good work." Okay, thank you. I will. Let's see. Cyberheart says next. He says, "Is there any cost to the speed increase with OpenVINO? Loss of accuracy?"
So...
And right, and of course, this is where the no free lunch law comes into play. But the cost is very small. Right, Raymond, as you've shown.
With the quantization, yes, and with the just pure the model conversion, all that, I don't remember seeing loss of accuracy at all because we actually parallelizing the pipelines of modifying the model itself. So the model will run exactly the same as if the original. It's just faster. So remember, I said that pi of
that's right,
the chart of that, So we didn't touch the model. We can still get better performance because we use the hardware more intelligently. Yeah. So
there is a bit of a free lunch, turns out. So yeah.
Yeah. Oh, there's a lunch there. People forgot it's a buffet. Just we didn't eat enough, guys. So it's like a huge line of like food we didn't know that it exists. So
yeah, Raymond, you're right. Like even in the examples I just showed, those are all at P32. So we haven't lost any accuracy, and we've got a significant speed up. Yeah.
Output should be identical, validated. Yeah, that's right.
Yeah, that's impressive. Okay.
Yeah.
Let's see. So Cyberhard says, "Is there any cost?" Oh no, I've already done that. All right, Fred Perimblokes. Is YOLO V8 free for commercial applications? Yes. So we offer two different licenses, AGPL and Enterprise. They are both available for commercial use. AGPL requires open sourcing your products. And we do this to keep a lot of the R&D in the open source sphere. This is great for kind of academic research, and it allows us to keep improving YOLO and keep giving back better models to the community. But if you'd like to develop in private and launch private applications for commercial use, then get in touch with us and we can work with you to get an enterprise license. Let's see. And then Gopala says, "Is YOLO V8 to Onyx conversion helpful to Intel Compute Stick 2? Raymond, over to you.
Let's see. What's the question again?
All right, let's see. He's talking about Intel Compute Stick 2.
Yeah.
I think that's Movidius, right?
Yeah, so we do support that, and then I would almost divert it to the new generation of processor. We have VPU built in. I think what we're doing here will be very beneficial for the new generation of the processor that will be launching in the coming months. Keep an eye on it, and we don't exactly shipping the neural stick that you talk about today, because we'll be moving forward into that. But if you are using it, you can feel free to come to me, and then we can help you to figure it out. Yeah, but like the new processor will have the neural stick built-in kind of. You can think about the VPU built into the processor, and then I think what you learn from there will be portable to the new generations. Same piece of code, basically. Yeah.
All right, interesting. And then let's see. I'm going to share my screen here for the next question. So I see. Where does model.xml come from?
The converted format. I forgot to mention it. It's my bad. The XML, the model, is basically when we do the model optimization. So when we have the Onyx or PyTorch native, we actually support later. Any TensorFlow, we will convert it into our own format. And that format is it's representation. So there's two pieces of puzzle here. One is the XML is the human readable component. So if you ever converted a format in OpenVINO, double click, you just see an XML file with all the, like how the weight looks like. And then the other one is the binary, which is the weight of the actual, the model, right? So there's like a .bin file and .xml file. Those are the two files that you would be generated when you're using OpenVINO. And we call the IR format, intermediate representation.
Okay.
Yeah, so that's what IR stands for. Yeah.
So I'm sharing my screen right now. This is so this is our Colab notebook, and this shows exactly how the export process works. So once you run the setup cell, which is really just doing pip install Ultralytics, we can run this one line, which is just YOLO export with the model, say OpenVINO. And so the interesting thing is we haven't actually installed any of these dependencies. We haven't installed Onyx yet or OpenVINO, but it catches that and it does it for us. Cool. So once it installs all the dependencies, it starts the export. And it's all done. So everything took about 14 seconds. And the cool thing is now we've got these predict, validate commands. And the XML file that we were asked about is right here. So if I
you can double click it. Yeah, you can double click it and open it, and you can see it.
Oh, we can actually open this?
Yeah. Cool.
Oh, it'll download it for me. But yeah, so this is XML that's human readable.
It's human readable. It's open on a browser easily.
Okay.
Yeah.
It'll open in a browser. Let's see. Open with Google Chrome.
Is fine. Yeah, browser.
Oh yeah. Okay.
So that's all the weights, the layers. If you go to the very bottom, that's the tricky part. A lot of people don't know. Let's go to the very bottom. Now we reveal the secret. You even know which format of the OpenVINO you use, like all this metadata is in here. You know which runtime you started at. So, and I just want the class names. You see what class names?
Oh yeah, even the class names. Well,
yeah. So all the secrets in there, guys.
Okay.
Yeah, that's why I said there's some classes name here that we can play about.
It's super interesting. Okay. All right, let me go back and see what other questions we got. All right. Let's see. Okay, Gopala says, please explain how the YOLO code will work. Oh, cool. Okay, so I just showed that. Or if you still want to see it, just go to our docs and search for OpenVINO. Okay, and then Asamoah says, how do you change hyperparameters in YOLO V8? Oh, okay, this is interesting. With YOLO V5, we had settings and parameters in a few different places, and we've centralized everything in YOLO V8. So from the command line, you can just write YOLO CFG, and it'll show you all your hyperparameters. They're in a single YAML file, and you can just change them right there. Or you can change their values at the command line. So you can say something like YOLO train, and then you can change LR0, which is your initial learning rate, to any value you want. And again, the docs are like a super resource for this. So you can simply go to the docs, and there's an entire page dedicated to hyperparameters and all of this. I'm going to paste that right here. It's called configuration. So go here, and all right, I'm pasting it right here. There you go. Oh, Cyberheart says great work on the docs. Thanks a lot. By the way, if you'd like to help us contribute, if there's any part of the docs that are missing, they're all also on the Ultralytics repo. It's all open source, so you can submit a PR and add or change docs content there. All right, now let's see here. I wonder how OpenVINO compares to SparseML. Okay, so SparseML is the Neural Magic effort. And Neural Magic is also an interesting company. They got dedicated quantization training and I think deployment tools. And so they are another way to take a trained model and run it faster, especially on CPUs. Their main ethos is targeting CPUs, since they say that that is the dominant hardware around the world, which makes sense. So if you want to have the biggest impact on, say, energy savings and AI models and running them faster, then CPUs is the target that you want. Okay, and let's see here. What do you think OpenVINO compares to CUDA? Alana is asking. Okay, so training and deployment really are two separate things. You can sort of run them similarly, but I would definitely recommend you do training on a CUDA device. It'll be much faster, and it'll allow you to iterate and experiment more rapidly, which is really crucial to getting a good result. But the deployment side is completely different. And oftentimes the deployment environment isn't suitable for a CUDA device. Or if it is, you could save a lot of money in terms of electricity and hardware by deploying your models on CPUs or even low power ARM processors. And this is really where all these export formats really shine. NVIDIA, of course, also makes smaller GPUs, Jetson devices, and even slightly larger ones like Orin. But if you can get away with it, there's no reason to spend extra electricity, spend extra hardware. So when you're coming up with a commercial application, you don't want the absolute best performance in your model, in your hardware. You want sort of the minimum performance that allows your product to kind of reach that MVP state. And you always think about how it has to scale. So whereas like a Jetson Nano might run your model nice, if you want to have, say, like 100,000 cameras deployed around the world, that's really going to cost you. And that kind of scaling is something that's going to be much more affordable on a low power device. So it really depends. If you're looking for like the absolute best performance, NVIDIA's definitely got it on their CUDA devices, but you're going to pay for it. And you may struggle to develop a reasonable business model around products with like CUDA edge devices. So. Okay, well, like I think that's it. Yeah, we've got, we just passed our hour. So there's a few more questions we didn't get to, but hey, just come to our GitHub, ask there, and we'll try and get you all the answers that you need, okay?
I want to flash one thing. I need to have this show because I would like to get a survey from everybody. The survey is where I'll get your feedback. And potentially we can give up some free gift next time, like a t-shirt. But today, if you do a survey, it will make my life a lot easier because I want to hear what's the top feature you want to get, what's the next thing you want to do, and this will help us to align our team to listen more. And thank you. Awesome. That's it. That's the flashy survey, and connect with us. Thank you.
Great. Well, thanks a lot for your walkthrough, Raymond. I think it helped me understand a lot. And thank you to everybody listening. If there's anything else you want to know, fill out the survey, let us know what your complaints are, what you'd like to see, or just raise an issue there on GitHub, and we'll get back to you. So thanks a lot, guys. Bye-bye.